So I will speak about some results derived with neutron monitor data and some space-borne instruments about the first GLE of the current solar cycle. The outline of my talk is brief introduction. After that, I will present the model for analysis of the strong SCPs and actually for this relatively weak GLEs using neutron monitor data. I will present the derived spectra and pitch angle distribution and some results of software and data, and finally I will conclude. So the study of these rare events, GLEs, there are only 73. It's very important, specifically the study of some parameters like the spectra and anisotropy. It's very important in order to reveal and to clarify the possible acceleration mechanisms, their propagation in the heliosphere, and nonetheless, they are important for some space weather issues, specifically the aviation dosimetry, some effects in atmosphere, and since they are differ to each other greatly, they are studying in a case-by-case basis. So this event occurred in 28th of October 2021. It was observed by several neutron monitor stations, specifically those that are in the polar region. And the greatest sign was observed by the Bayer neutron monitor in Domsey. Some rapid rise was observed by Fort Smith South Pole Pivanuk neutron monitors, and as well as by the GOES, increase in all the channels, and the flux remained above the background level for about 4.0 hours. So it formally corresponds to this proposed definition by our group that it should be observed by at least 2 neutron monitors and a space probe. So let's move to the method that we are employing for the GLE analysis using the neutron monitor data. We employ the fact that the monitors located inside the geomagnetosphere are sensitive to different asymptotic directions of approach, and also to different part of the rigidity spectra. So we are using the magnetosphere as a giant spectrometer, and by modeling the global neutron monitor response and optimizing over the experimental data points, we can derive the necessary information. So we are using the relation, the count rates of a single neutron monitor is the integral product of the yield function of the monitor with the primary spectrum, where this guy, the specific yield function, it's counting the effective detector area, including the registration efficiency of the monitor itself with the particle flux at a given observation level. So it accounts for the full complexity of the atmospheric cascade. In our model, we are modeling the contribution of the vertically incident particles, and as was pointed some 20 years ago by John Clem, we are considering also the oblique events from different sectors. So the count rate increase due to the ACPs is the integral product of the assumed spectrum, the specific yield function, the atmospheric, the magnetospheric transmissivity, and this term, it's accounting the anisotropy, and over the background, which is due to the galactic cosmic rays. So the steps are, first we are computing the asymptotic directions and the cutoff rigidities of each station. We are modeling using this expression the response of each monitor, and after that, with convenient parameterization, we are deriving the energy spectrum, anisotropy axis duration, and the pitch angle distribution. So in the model, we can assume different type of spectra, a modified or pure power or rigidity spectrum, an exponential one, the Ellison-Ramati or band function, whereas the pitch angle distribution is usually modeled with Gaussian-like distribution, and it results from about 5 to 14 parameters. It depends on the complexity of the assumed model. Some example, this is the compute asymptotic directions for several neutron monitors. Here it's in the rigidity range between 1 and 5 gigavolts, which correspond the expected maximum signal, whilst in the modeling we are assuming the upper limit of 20 gigavolts. Note that here the crosses representing the interplanetary magnetic field direction measured by the ACE space probe, and it's relatively it's shifted for about 60 degrees from the derived apparent position, which implies some diffusion of during the propagation. The derived spectra, this we have a 1 minute spectra derived in our paper, just appeared 2 weeks ago in solar physics. Here are just several examples of during different moments of the spectra, which will relatively soft with considerable roll-off, so very notable steepening in the high energy range, and a constant softening of the spectra was derived during the event, and the steepening remains slightly diminished and in practice vanished in the very late phase of the event. The derived pitch angle distribution was relatively broad. It's not like beam like some other events or the 2 previous events when we observed a very complicated angular distribution of the GLE particles. Here it's nothing dramatic, but relatively broad distribution, and steady and slowly broadening out of the distribution was derived. So for the next step, we are computing the networks of the producing protons, which somehow it's related with the injection spectra of the sun. And here you can see the prompt component and the delay component, how the steepening is changing and its practice vanishing in the late phase compared with the Calgary neutron monitor. And in the next plot are presented the derived coordinates in GAC coordinates of the anisotropy axis and compared with the ACE measurements of the magnetic field, and you can see that the event occurred in very complicated interplanetary magnetic field conditions. Accordingly, the average angle between the proton flux and the magnetic field is also presented, and which changes throughout the event from some 50 degrees to about 90 degrees, nearly to the maximal phase, maximal net flux of the event. And here it implies that actually we have propagation across the field of the GLE protons. The next plot is presenting the Soho-Ernehet data. First in the upper plot in the deca MeV protons during different moments of the event, some rise, decline, and another rise. And this is an illustration of the complicated interplanetary magnetic field conditions derived by the on the basis of the ACE satellite, and you can see that we are shifting the Soho-Ernehet data to the orbiter phase, and accordingly to the characteristic of the GLE producing protons, that to the Earth, from the Earth to the Earth. So the timing is somehow consistent, and in this plot are once again you can see the increasing of the how the spectrum softened throughout the event, and accordingly the steepening of the spectrum is vanishing. And in the last spot, we are presenting some sectoral intensities of the RNA-head observed protons in different sectors, the zenith, south, west, and northwest. And for the deca MeV protons, and the same for two anisotropy indexes of the producing GLE protons deduced from the neutron monitor network. And you can see that, in fact, the deca MeV particles, they exhibit much more anisotropy comparing to the neutron monitor. This implies possible two populations, and considering the timing that we are studying with using the space probes, so these anisotropy characteristics, we can claim that the delayed components of the deca MeV protons are accelerated of a distance of about 5 solar radii, most likely in by shocks of the CMEs interacting with the solar wind, whilst by the timing of the relativistic neutron protons that are registered by the neutron monitor network, so they are accelerated at distance of less than 1.5 solar radii, and considering that they are arriving mostly of the southward, where the flare region was observed. So the prompt component is most likely accelerated in the corona. So this is my conclusion. Using a verified neutron monitor yield function, and also a verified method for by direct space-borne measurements for previous event, we are derived with high resolution the neutron monitor, the spectra and angular distribution of GLE 73, and on the basis of the SOHO RNA data and the timing, we are distinguishing two different components with different origin of the arriving solar proton in the vicinity of the Earth. Thank you. It's a nice picture from OO.